This presentation has been a monster to put together.
Give them the man hours
Well,
for both of us.
Hundreds and hundreds. For myself, I said earlier 175.
So these are the people responsible for the electrical world that we have today. And I thought it fitting to paste their pictures on the American Indian archetype of the Tesla four-phase system. But Morgan stuck with Edison, even though all the experts of the day said that Edison was full of it. Morgan stuck with them and got them going. And then on the other end, we got in the black-white quadrant, we have Nikola Tesla, and Westinghouse was basically the one that funded him. So Westinghouse and Tesla, Tesla was the key to the electrical power system as it is today. Not only can it be used for light, but it can be used for motors, and it's not direct current, so that it can be transmitted over longer distances and have a definite frequency, which was a big step forward. So this is the original mess of the telegraph and arc light wiring days. It was just, it was overwhelming, absolutely overwhelming. There's just wires everywhere tied to everything. They didn't know who, what, or where. So the issue became something of significance when one of the linemen got caught in the indeterminate mess up there and did the big burn down. And the barbecue event really caught the news people's attention. And then we have the episodes of all these million-dollar devices that we buy from China. The first day that you try to activate them, this happens. An electromagnetic transmission structure, by definition, you should be able to see clearly from one end of it to the other without obstruction. If there's an obstruction, that constitutes a short circuit. The metal is the opposite. This one we got in the conductors and insulators. We talked about this, is the reflector. So what the electromagnetic boundary condition does is it creates a condition in which the electricity is trapped between the conductors. And then the geometry, the spacing and the diameter, so the diameter is the counterspatial element and the spacing of the wires is the spatial element, is that determines the coefficients that we call inductance and capacitance. So in this case, we can take electric power, which is the quantity of electric induction divided by the product of the inductance and capacitance in that little slab of dielectric. Now, if I connect a battery to this set of wires, and let's say it's open at the other end of the line, a current will flow into this line even though there's nothing connected to the other end of the line. This is an interesting characteristic of an electromagnetic line, and there will be a definite current. And that definite current will be the characteristic impedance of the line. So what will happen is this line will look like a resistor, and energy will be sucked out of the battery to fill the ether or space all the way to the end of the line. And then when it gets to the other end of the line, the current will find that it has nowhere to go, and it'll turn upside down. And then it'll start heading back. So if we wait 2 light seconds, we will find that the current will drop significantly in a step when that negative current wave comes back 2 seconds later to the sending end of the line. So this is a very important concept in power transmission, and this is why impedances have to be matched. And so that way, then the power that you're putting into the line is its natural power, and there's no fighting of it. It just flows naturally, and no forces are exerted on the conductors. In this case, the current is not constant, but the potential is. So the current diminishes as you go down the line. The potential remains constant as you go down the line. So you can kind of see these are two reciprocal forms of electrical distribution, and that's why I'm doing this, is to show you the two sides of electrical transmission. It's important to understand both sides. And we already have a bit of a mathematical understanding of how this impedance determines the short circuit current. I've experienced small ones in my face, been in neighborhoods where I could have had bigger ones. This is a bigger one. 2400 volt system. This is a delta Y. On the way up here, you can see the secondary bushings on the transformer. One of them goes up to the phase conductors, and the other one bonds to the tank and connects to the substation ground plane. But also there's a neutral, so what they're doing here is the idiots, they're running all of their zero sequence current because it's a 4-wire Y-connected load, all has to flow through the substation metallic structure before it can find its way back to the transformer, which is nonsensical. This is the bad way of doing things. This is how it's hooked up. Everything today is being modified to this system, YY. Here's a YY system for an FAA station. Sometimes, like in this case, you just use a big reactance coil. Now there's other transformers in the system that run the meters and the relays and all watt meters and kilowatt hours and all that stuff. So in this case, you can't hook your amp meter to a 5,000 amp cable, but if you put a current core transformer around it and the ratio of the turns, if you have, in this case, how many turns? If there's 10 amps flowing in the primary, in the wire, and you have 10 turns, then there will only be 1 amp flowing in the meter. Well, DWP always does everything the old way. That's why their systems are the only ones standing after the blast or the hurricane or whatever. Their stuff's still standing, everybody else's stuff is strewn across the desert. This is kind of how they do it now. That's a cluster of current transformers and potential transformers. Here's the ones at that delta substation with the grounding transformer. Because the load is delta, the current transformers are open delta and the potential transformers are open delta. You can see the potential transformers there in the front, the 2 insulators, and then current transformers, the old style, up on the tower in the back in the red. Then we have the Then we have the open system, the Y. We can phase that in the same coordinates as the delta. We got the star-David connection now going between one set of windings and the other. This is like a delta primary, delta secondary with a phase reversal. Saw this used on the California electric line. And this is the normal delta to Y transformation. And then ungrounded systems, we already talked about how they can charge up like capacitors. And then through the arc hysteresis, they can really develop some rather serious raucous waveforms that burn shit up. That's why you usually ground the things, or at least through a resistor, if nothing else. This is the way that the voltage magnifies is each time the arc jumps to ground, it charges the system one polarity and the other, and always leaves some DC behind until the line has a rather considerable amount of voltage on it. These are some of the older variety of mercury arc rectifiers. These things are really colorful and fascinating. This is one of the original ones. I'd love to get one of these things. And here's how they operate.